We need to be able to afford a technical director kind of thing.
I thought that was a Dave job.
He's our call screener, technically, and he does a fantastic job. We have never had an inappropriate call come through.
Shot them down.
Okay, we're live again.
Okay, we're live.
Welcome to Sidewalk Science. Hopefully we'll get some of our other scientists to join us, with this inclement weather that's been buffeting the United States. It's understandable that some people are having trouble getting connected and staying warm and all kinds of stuff. In fact, that might, well, I don't know. I've got perhaps some ice dam damage on my roof. Even in Illinois, this is an outlier. This is 2 standard deviations beyond the norm in terms of inclement weather.
Well, the last big one like this was what, 87?
Something like that, yeah.
I remember it didn't work.
Right. Well, welcome to Sidewalk Science. Maybe one of the things, I hadn't planned on this previously, but it just comes to mind to talk about why a very cold continental air mass is a reasonable consequence of global climate change and global warming.
Oops, I have a dog here.
So we can talk about that. We can talk about the news of Mars.
Oh yeah, 3 in or around Mars, on or around.
And a helicopter.
Yes.
Isn't that amazing? And then you had some news you wanted to talk about with the polar magnetic flip that
is occurring, and a suggestion that it caused all sorts of problems 42,000 years ago.
Yeah, for Neanderthals especially.
Well, I like the title. It says after 42,000 years, the flip occurred 42,000 years ago, and then Neanderthals died. And I go, and my grandfather died too. Right. I mean,
well, it's one of the truisms of science that correlation is not causation, right? And all scientists have to be very careful about that. Just because 2 things are correlated in space or time does not necessarily mean that they're related at all, much less that one causes the other.
And that we know that Neanderthals were alive and well roughly 18,000 years ago in France. So.
I have using the are we using the right microphone? Our technical assistant asks. So let me check that out.
You sound good.
Do I do you? Okay. Let's see, make this window a little smaller. Let me check to make sure which microphone I'm using. Here we go. Microphone is microphone array built in. Oh, let's use this. Let's use the web. Maybe we can use the webcam. That one doesn't have a microphone. It doesn't that broadcasts. Is it? Can you still hear us, John?
Yes. Yes.
Sound any different?
Yes, you have a little bit more bass.
Oh, good. Okay. Excellent. I like that. I am the voice from the bass.
You are my son.
Luke, I am your father. All right. So without further ado, let's see, what shall we talk about first? Ivan or John, do you have a preferred topic or maybe your own that you'd like to chew on for a minute?
I don't know. I've just been working on my usual kind of thing, an X-ray spectrometer, and checking out, reminding myself of K fluorescence edges. And I pull up this chart of K fluorescence edges, and it's actually up on this screen over here. And it amuses me because it's a periodic table. Mm-hmm. Now, K fluorescence is not periodic.
Could you tell us what K fluorescence is?
K fluorescence is when you pull an electron out of the very innermost shell of an atom, the shell of electrons that's closest to the nucleus. And then another electron from the next shell out, the L shell, falls into the K shell and an X-ray comes out.
Okay.
Okay. And the periodic table is about phenomena that have to do with the outermost shell in the atom.
That makes sense. Yeah.
Okay. K fluorescence has to do with the innermost shell of the atom,
Which should be shielded from chemical-like stuff.
which is shielded from chemistry. I mean, you know, if you go to very light elements, you see slight chemical shifts in K fluorescence, but it's not a large effect, and it's not in this table at all. But the table is still organized as a periodic table. And I think it's a cultural thing. You know, we have become so used to displaying the properties of the elements as a periodic table that we feel compelled to do it even when it doesn't make any sense at all.
Right.
So what is the rationale for the arrangement of that table that you have to review?
Well, the table is your classic chemical periodic table. The actual numbers in it, well, the K fluorescence energies are, there's some small physical effects that affect them slightly, but they're basically just proportional to the square of the atomic number. Okay.
Is that the number of protons and neutrons combined?
No, just the protons.
Just the protons. Thank you. Yeah, so that's how tightly bound. The number of protons might dictate how strong the electric attraction is between the nucleus and the innermost electron.
Yes. Yeah. Yes. That's exactly what it is. And it doesn't, because it's the innermost electron, it doesn't notice what's going on the outside. And so it just, the energy is just dependent on the atomic number.
I'm sitting here wondering, how do you get there?
Yeah.
You've got this huge envelope of energies just sort of everywhere.
How do you target?
How do you get inside of all of that to get those two innermost?
How do you pull out the innermost electron?
Yeah.
Well, it's actually very easy. What you do is you fire in a photon that is a bit higher in energy than that electron has. And the interaction between the photon and the electrons in the atom is, for a high energy photon, is pretty weak until you get into the inner shell. Or what kind of happens is that you can think of the nucleus holding the electron still while the photon hits it. Whereas for the outer shell electrons, the photon, there's kind of spread out, and the photon goes right through.
Yeah.
And so you send in a 10 kilovolt electron into an iron atom.
You mean electron or gamma ray?
Oh, sorry, a 10 kilovolt gamma ray into an iron atom, and out pops an electron, and pretty soon after that, out pops a 7 kilovolt X-ray. Now you can do it with charged particles too, and if you hit atoms with alpha particles, similar things happen, and you often manage to kick out an inner shell electron, and you see K fluorescence.
Okay.
And where is this leading us? Where does this research end up?
Well, this particular thing is intended to use X-rays emitted by the sun to excite minerals on the lunar surface and probe their composition.
Wow.
So, the energy of the X-ray you get out depends on what element is present.
Yeah.
And so the plan is to use X-rays from the sun as the exciting thing, and look at the lunar surface with a spectrometer and see what the lunar surface is made of. And this is not a new idea; it's been done, but this is for one of the soon to be we're building an instrument. We don't quite know what the platform it's gonna sit on will be like. It's supposed to sit on some sort of mini rover that will go around and look and survey the region around a lander.
Well, that same process, could it work on, oh, I don't know, Mars?
Yes. Yes.
Excellent.
It also works for asteroids.
Oh,
And
they make medicine for that.
They do. Yeah.
And I was a bit involved in the OSIRIS-REx mission. And it had an instrument that looked at fluorescence from the asteroid.
Okay.
Yeah, there was a recent, again, you hate to say it, but discovery, that there's a suggestion that the rock that hit us to wipe out the dinosaurs was not an actual meteor, it was an asteroid. And I'm going, and the difference is what?
Well, they're thinking it may have come from the Oort cloud.
Once we get hit, does it really make a difference as to
Where it came
from? Because the Oort cloud, yeah, it's way out there, and then there's this other one, and this other one, and they're basically all just big rocks floating around, and we're a target.
Well, the stuff in the Oort cloud isn't rocks; it's more like snowballs. And
well, but the thing that hit us was a rock.
Well, it had some rock in it.
Yeah, and we can actually go down and dig it. I mean,
yeah, it had some rock in it, but exactly what it was made of is not completely clear. And yeah, this idea has been around for a long time. One of the things is if you want to really clobber the Earth, clobber it with a comet, because the relative velocities of comets that cross the Earth's orbits are much larger.
Mm-hmm.
Because comets fall in from every direction. Asteroids tend to be in orbits that are fairly similar to the Earth. So the Earth is going around and the asteroid's going around, and you kind of join like that. Whereas a comet can come in head on.
Oh, yeah. and they do.
Yeah, that would be a bad day.
Oh, bad day on planet Earth.
Yeah.
That would be a bad day. And unfortunately, there's been a great deal of planetary defense effort in the last couple of decades cataloging the asteroids that might hit the Earth.
Yeah.
And that's been a very successful effort. And we pretty much know that we will not be hit by a large asteroid anytime soon.
Good.
Yeah.
The trouble is that a comet could sneak up on us in a way that we wouldn't even know about it until a few days before it hit.
Oh my goodness.
Yeah,
Well,
this is why I said discovery, because it's been around for years, all sorts of potential explanations, and we've looked at them and we keep going, and the best we can see is that, the crater is there. We can look at it. We can go down inside of it and look at the material that is left, and we see the rocky material, and we see the crater, and we see all, but is it definitive? And the answer is, well, not really. That still leaves everything open. And so this new discovery isn't new. It's something we've been batting around for years.
Yeah, it's just more, so maybe a more appropriate way to frame it and the headlines is additional evidence or confirmatory evidence or something.
But that doesn't make good headlines.
Right. Yeah, true. It's one of the topics that I wanted to bring up in general in our conversation, and that is, the sensationalism of science headlines sometimes makes it like, makes it seem like this is a definitive, proven new thing. And, because the press tends to grab hold of headlines from scientific journals and things that universities and research labs put out as press releases, the tentative nature of science and scientific discoveries is often lost in the sensationalism.
Yeah, because tentative doesn't sell newspapers.
That's true.
And again, we couch things all the time. That's how we work. We think that this is true, and here's the evidence that I have for this explanation. And now we have a scientific debate going on as to who's doing what, and there's a new experiment here, and there's a new one over there, and we slowly but surely come to a conclusion, and then someone comes along and goes, but wait.
Yeah. Well, I think, I think this is one of Ivan's areas of concern, is how do we come to conclusions based on evidence? When we have a new discovery, or when we have some new piece of the puzzle, how do we figure out the way it fits with other pre-existing pieces of the puzzle? Ivan, is that something that you're concerned with?
Yeah, as an aside, I'm reminded of Betteridge's law of headlines, which is if you have a headline that ends in a question mark, you can generally answer it with the word no. You also see a lot of headlines that say scientists say X, which is usually means there are like 3 scientists that wrote a paper together say X. But yeah, usually it seems that you need to try and understand what the scientific consensus is, if there is one, right? Sometimes there isn't a consensus, or the consensus is weak. So the consensus regarding the source of the asteroid that hit 65 million years ago, as I understand it, it's based on the likelihood of a collision with an asteroid versus something from the Oort cloud. And the new discovery had to do with simulating what happens if a comet flies close to the sun and breaks up. And then it turns out that the fragments are in orbits that are not so dissimilar, and then that increases the probability, right? So, but it's not a strong inference.
No.
So in general, you should look for what is the scientific consensus, because unless you are a scientist working in that field on that problem, you're unlikely to do better than the scientific consensus.
No. This is when we turn to those people who've actually been studying it and say, what do you think? And then a lot of people just sit back and go, well.
For any given question, right, you're going to have scientists who, a certain percentage of scientists that just get the answer wrong, right? So if you ask a random scientist about a question which has been in the news, maybe you have a 90% chance of getting an answer that goes with the consensus, if there's a strong consensus. But it also means that if you're reading about a view that disagrees with the consensus, you can almost always find a scientist somewhere who will disagree with the consensus.
Right.
And I'm not saying that everyone has to agree with the consensus. If you're an expert and you have reason for your point of view, you may be championing a different perspective, right? But it does mean that you shouldn't be cherry picking your scientists based on their opinion.
Well, it is a strategy for a scientist. I remember the late Tommy Gold, who was almost always wrong, but when he was right, he was spectacularly right. It's a strategy.
To be a contrarian was his strategy then?
To be a contrarian was his strategy.
Yeah.
And, he was like the baseball player who comes up and swings for the fences every time, and he usually strikes out, but every once in a while he hits a home run,
Yeah. Well, we see this in the philosophy of science, and when we deal with issues of critical thinking and skepticism, we see this a lot. Yeah. I believe Carl Sagan had a quote that said, a lot of people claim that they laughed at Christopher Columbus and they laughed at Galileo and they laughed at Copernicus, but they also laugh at Bozo the Clown.
Yes. Yes.
And the chances that a radically heterodox opinion or I guess, no, it would be unorthodox opinion.
Yeah,
Un-
no one, yeah.
The probability that a radically unorthodox opinion will overturn the consensus is really low. It does happen sometimes, but another thing that Carl Sagan made famous is the idea that extraordinary claims require extraordinary evidence. So just because you have a contrarian point of view and you have an inkling about maybe why everybody else is wrong, you need more than an inkling.
Yeah, and this gets us all into that whole QAnon thing that's going on now, and even in Congress, that there's these wild speculations of absolutely inane things with no evidence whatsoever. It's just out there, and you begin to wonder, where is the common sense? Well, not common sense. Where is the thought processes going in here? Where's the critical thinking? Right. Where is the evidence for A or B or C? And it seems to me that we're losing it, that what we had done years ago in our educational system was have a perspective of knowledge based on when I was growing up, which is, of course, there were still the dinosaurs running around. You know, you remember them, John.
Unfeathered, though.
Unfeathered dinosaurs, yes. And we were taught that you had to have evidence in order to propose anything. And just sitting there and blurting things out was not a way of getting your opinion across. And now it seems to be the logical way of doing everything, the norm of politics and of television and all of our entertainment media.
Well, Ivan has done a lot of thinking about this too, and he, I don't want to put words in his mouth, but going beyond just recognizing logical fallacies and thinking critically, there are mechanisms available to us to determine the plausibility of arguments. So, Ivan, back to you.
So I'm going to make the first public announcement of my book.
Textbook Rationality, yes.
Textbook Rationality. So my view on education, Joanne, is that those things were never really taught. Like in elite circles, like among scientists, yes, critical thinking, you need evidence to support your point of view. It's part of scientific culture. But I don't think was it ever taught as culture in general? I don't think rationality has ever really been taught in schools. It's most especially inductive rationality, right? So we do a lot of deductive inference in schools. When you're doing math problems, you're given some axioms, and then you calculate the answer, and the answer is either right or wrong. And if it's wrong, it's because it contradicts the axioms in some way, right? But induction, we don't really teach induction at all. In science class, they give you the nice flow chart, right? Which is you make some observations and then you come up with a hypothesis and you test the hypothesis. And if the test fails, you go back and come up with a new hypothesis. Okay, but where does your hypothesis come from? And what constitutes a test of the hypothesis?
And what do you do with data, both confirmatory and disconfirmatory?
Right.
Yeah, we're always confirmatory and never disconfirmatory.
Most of the famous examples in science of discoveries are discoveries where the answer made the conclusion obvious. Like the alternative was inconsistent with the result. But that's not the way most scientific evidence is, right? Usually you have two competing theories and they can both explain a given observation. But one predicts it with a greater likelihood. And so that's why that experiment leads you to have more confidence in that particular theory. So we don't actually teach rationality in school. We don't teach a whole lot of critical thinking in high schools.
No, never.
But teachers have been talking about critical thinking for a long time. And one strategy for doing that is to teach, critical thinking about history in history class. So in other words, instead of having a dedicated class on critical thinking, you're going to teach critical thinking in little pieces in the different classes that you teach. But one of the things about rationality is it's difficult to teach and get used to in a general way, right? So if I spend all of my time doing critical thinking about building software, then I have a lot of feedback. And if I make mistakes, I know about it. And so I get an intuition for what good criticism is like. But if you then ask me, hey, here's this medical diagnostic problem, well, intuitively, I'm going to be terrible at that because I don't do that all the time, right? So if you're a scientist and you work on a very specific problem, you're probably going to be good at thinking rationally about that problem. But as soon as you go to a different problem, it's going to be much more difficult. And it's going to be even more difficult if we don't teach you what rational thinking is.
Right.
And we
Well,
don't
that's one of the advantages that I in particular had. Again, you go back to the old days, and our schools were segregated, if you will, by intellect. So there was the 5th level, 4th, 3rd, and so there were 5 different levels. And I was always in the geek level. So we were always in this advanced area of thinking where we were bantering back and forth with the professors at school. And there was an awful lot of again, inductive as well as deductive reasoning. And so perhaps I was fortunate. And again, I look at it from a very, very isolated point of view of a rich white kid in a rich white community.
Well, I had a similar experience. I took a phenomenally, probably one of the best classes I ever had, and it was in high school. And it was advanced placement English, of all things. Now, here I am, I became a scientist, but my favorite class in high school was an English class. And one of the reasons was it covered things like mythology, which was fun to learn about, but it spent, I think, more than half the time teaching us about logical fallacies and how to apply critical thinking to analysis. So one of the things we'd do is we'd watch commercials and we'd try to spot the logical fallacies in commercials. But the reason I'm bringing it up specifically is because it was the advanced placement English course. It was the English course for the people who had already displayed a competency for intellectual analysis. And, you know, to resonate with what Ivan is saying, my goodness, we need everybody to be able to recognize basic logical fallacies and understand how rational thinking is done, ways to approach decision making.
My thesis for years that critical thinking is teachable. It's a skill set.
It was your thesis.
In fact, it was my dissertation. And I see no reason why children can't be taught these basic skills in the same way that we teach reading and basic math and all these other things, because it's just an approach to how to find out information.
Yeah. Is that what your book's about, Ivan?
Basically.
In part, right? So one you know, we just talked about logical fallacies. So the logical fallacies in general are fallacies of deductive logic. So one example is the argument from authority. You know, this is true because this authority over here says
because
so.
I'm good.
And deductively, this is a fallacy in the sense that it is not guaranteed that someone who is an authority is correct. However, it's not really an inductive fallacy, right? So if you are having a health problem, go to the doctor and do what the doctor says because they are an authority. They have expertise, right? And I think that this is a big issue today. Is there is a widespread rejection of expertise, of legitimate expertise, right? So my book is about is really 3 things. The first is talking about this invisibility, this sort of absence of rationality in culture in general. Rationality is a word that gets used for a lot of different things, right? This is the way I always thought about it. And, I've been in, I have a PhD in physics, and I've been involved in science and critical thinking outreach for a long time. So I was very surprised to read about the Bayesian definition of rational thinking, and also about cognitive bias. So most cognitive biases, most of them are inductive biases, right? So there's logical fallacies for deduction, and cognitive biases.
True, then this must be true.
For induction, right?
Can you give us an example of a bias, a critical thinking fallacy that entails inductive reasoning?
Yeah, so here is one example. A good example might be the gambler's fallacy, right? So if I have a coin, a fair coin, and I flip the coin 5 times and I get heads 5 times in a row, what is the probability that it will be tails on the next flip, right? It's been 5 times in a row that it's been heads, but it's a fair coin.
So it's building up a lot of pent up tailness.
Right. In fact, in Las Vegas, the last time I was in Las Vegas, which was years ago, at the roulette tables, they have a digital sign that shows you what numbers came up recently, if that should make any difference.
Yes. Yeah.
And if it did, then they're cheating, right?
Exactly.
So yes. So the gambler's fallacy is that people expect a sequence of random numbers to look random. And our sense of what is random can lead us astray, right?
Yeah,
and
we're not very good at intuitively recognizing or even producing a random string of numbers. One of my common responses, somebody says, pick a number between 1 and 10, and I'll say pi over 2.
Yeah. And watch them go.
Ivan, have you seen this diagram? You ever seen that one?
I have not.
This is from an essay by R.A. Littleton called The Nature of Knowledge. And he talks about having your certainty about things be represented by a bead on a wire. And as you think that it's more likely, you move your bead toward one end of the wire. And if you think it's less likely, you move your bead toward the other end of the wire. And he notes that the greatest problem is that people let the bead fall off the end of the wire.
This is a true statement.
So look up Littleton's bead sometime. There's the text of this is online. It's the illustration unfortunately is not. It's from this book here. The Encyclopedia of Ignorance.
Yeah,
this is a fun book.
Yeah, that is an important problem. To sum up, just to talk about what rationality is, like among people in cognitive science and behavioral economics and AI, thinking in a Bayesian fashion, which means consistent with Bayes' theorem in probability theory, is considered to be sort of a gold standard in rational thinking.
Ivan, for our viewers that may not know what you mean when you say Bayesian, can you give us a 2-minute synopsis? I don't know if it's possible in 2 minutes. But.
Yeah. So relative to the bead idea that John was talking about, right. If you have let's say that the 2 ends of the wire correspond to 2 different theories. It's the asteroid that hit the Earth came from the asteroid belt, or it came from the Oort cloud.
Excellent.
Right. And this bead, most people have a tendency to go, you know what? I've decided it looks like trajectories are much more likely to hit from the asteroid cloud, the asteroid belt. So I'm going to put my bead all the way over to here.
And it falls off the end.
Right. Whereas what should happen is, as you get a piece of evidence, You're supposed to move the bead towards one side or the other.
No matter where it starts, right?
No matter where it starts. And in fact, if you have access to enough evidence, you could probably let the bead start anywhere and it will just go to one side or the other. More so, it will never fall off the ends, though. It will never hit the end. Now, probably. I'm much more careful now when I use the word never. I always say probably at the end.
Well, I did once attend a lecture by Feynman where he was talking about the uses of negative probabilities and probabilities greater than 1.
Oh my goodness.
Oh, how did he do that?
So
I'm just going to melt.
What Bayes' theorem says is that if the probability of one of your theories, that one of your theories is true, goes up, then the probability that the alternative theories are true must go down. And this relationship tells you, given some evidence, how far you should move the bead.
And that you can't move it in 2 directions at once.
Right.
Well, you can. You can make a multi-dimensional Bayesian landscape, sure. You can move it. It can be a bead on a table, and you can move it in.
Yeah, it moves in one direction. That direction may track against multiple axes.
Yes.
Yes.
Yes. But the truth is that to really do it right, the bead has to be a cloud, and it can happen that you're wiggling the cloud around, and it can happen that the cloud's concentrated in 2 different places.
Right. Like the height of Americans concentrated in a bump for females and a bump for males, right?
Yeah.
So part of the existence of this ideal notion of rational thinking means that we can make a distinction between rationality and critical thinking, right? If we didn't have this, then being rational would be something like maximal critical thinking.
Yes.
But if we had an ideal thinking machine, it could use Bayesian reasoning and come up with an answer that didn't need to be criticized because all the grounds on which it would be criticized were already built in.
Hmm.
But for humans, humans leap to conclusions. We have, preconceptions. We are not nearly as careful. And so for humans to be rational, we need to think critically. But my own experience has been that ideal rationality gives you a conceptual framework on which you can hang things like cognitive biases and logical fallacies and inferences and all forms of critical thinking. So the last part of the book sort of returns to the basics of critical thinking and says, look, if we want to be rational as humans, we need to apply a lot of the conventional thinking about critical thinking. But it's really this idea that overall in the book is the idea that rationality is treated like a soft skill.
Yes.
Right? So if you ask someone, was that rational, or what does it mean to be rational? They'll sort of say, well, it means like logical, or maybe it means scientific. But it's a very vague idea. And a lot of people treat it as, I'm rational if I am being reflective, if I gave this a lot of thought.
Or did my own research.
Yeah.
or if I can find a reason for my belief.
Any reason.
Right. Any reason.
I looked it up on the internet.
Yeah. And rationality is more than that. Rationality is at the very least, it is the balance of reasons.
Right. Oh, I like that. One of the things that, tell me if I'm on the right wire with my bead here, Ivan. One of the things that I've considered when thinking about Bayesian approaches to problem solving is that unlike a flipped coin, which has no memory of its prior state, and its prior state is irrelevant to its future state, in Bayesian reasoning, prior evidence can be highly relevant to the characterization of a system. You don't start from scratch every time you collect a new piece of evidence, that you must take into account the history of evidence, either for or against a proposition. Is that correct?
Yes. So, and this is where you get, you know, the statement, extraordinary claims require extraordinary evidence is not just a, you know, it's not just a guideline, right? If from a Bayesian perspective, what you're saying is that the huge weight of evidence that you have so far supports this theory so well that any new piece of evidence is more likely to be noise than to be able to offset this massive weight of evidence that you've accumulated.
A new piece of contradictory evidence, maybe.
New piece of contradictory evidence, right? I illustrate that in the book with a dice game, which was kind of the simplest scenario that I can come up with. It's of course oversimplified compared to the real world, but as a teaching tool, it kind of illustrates the idea that a theory that is more restrictive in what it predicts will beat another theory that has, you know, can predict more phenomena, as long as the actual data can be explained by the first theory. So a more restrictive theory beats a more flexible theory as long as the data fits within the more specific theory. So the example would be this: if I have got my 6-sided die and my 20-sided die.
There you go.
And I pick a die at random.
Okay.
Which die did I pick? Like, what is the probability that I pick the 6-sided die?
50-50.
Yeah,
Right.
50-50. Right.
Okay, but now I'm going to roll the die, and I tell you what I rolled. I rolled a 1. So now you have more information.
But
So it's
isn't
probably the 6-sided die, because 6-sided die has,
it's only 1 in 6, whereas the 20 is 1 in 20.
yeah.
Right.
So there's a
So-
higher chance of the 6-sided die rolling a
Yeah.
1 than there is the chance of the 20-sided die.
Right. It turns out to be there's a 77% chance that it's this 6-sided die. Now, if I take the same die,
Aha, it was the 6-sided die. You just showed it to us.
okay, pretend I didn't do that. If I take the same die and I roll it another 14 times,
Yeah.
and every time the number comes up between 1 and 6, now you're much more confident that it's the 6-sided die.
Yeah, confident.
Every successive roll. So unlike the successive flips of the coin, the successive rolls of the dice can tell you more about the system you're analyzing, right?
Well, the reason I'll come back to the coin example. The reason it is in fact just like a coin, right? But it's like, am I dealing with a fair coin or an unfair coin? But I'll go down that road later on. But in this case, we're saying we know what the two theories are, right? And the two theories make different predictions. And when you get a lot of data consistent with one theory, the narrower theory, in this case is the 6-sided die, it predicts fewer possible outcomes, right? Only 1 through 6. Whereas the 20-sided die can account for every one of those rolls, but it can also account for a lot of stuff that didn't happen. And as a result, it turns out that means the probability of rolling a 1 through 6 on a 20-sided die 14 times in a row
Really low.
is 1 in 20 million.
Wow.
That's really low.
Yeah. So I have a related question for you. I don't want to distract you from getting back to your fair coin example. If we can put that on the table for a second. My question about Bayesian reasoning is, I have a lot of friends who have an aversion to mathematics and mathematical thinking.
That's
Is
unacceptable.
Okay, so that's just not gonna, you just don't allow that. Okay. So is there a way that my non-mathematical friends can apply lessons learned from Bayesian reasoning?
There is nothing mathematical in Littleton's presentation, but where I showed you the diagram.
Right.
There's no equations. There's no nothing. It's just, hey, you
Hey,
have some evidence, move your bead. Don't let it fall off the end of the wire.
I just got news that Mike Albro has joined us and Abby will be here momentarily. Might wait a minute for Abby to join. I think she's in the holding room with our moderator, Dave, probably talking about very important things. And
like how much snow was in New England?
yeah, here comes Abby.
Oh, there wasn't that much, few inches.
Oh, we got it. We got it all.
Yeah.
Big
We-
deal.
We'd love to send some to you, but
It's okay. It's okay. I grew up in Rochester, New York. I got as much as I ever wanted.
So welcome, Abby and Mike. I want to spend just 20 seconds to catch you up for our conversation. We have kind of a theme today, and we've been talking a lot with Ivan about the notion of rationality, and he's specifically introducing us to some of the concepts about Bayesian reasoning, which takes into account the way that both confirmatory and disconfirmatory evidence can accumulate to make one conclusion or hypothesis more plausible than another.
oh, that was a good explanation.
Thank you. And I had just asked Ivan the very penetrating question, what about my friends who don't like mathematics? Can they still apply lessons learned for life skills apropos to Bayesian reasoning?
He takes a deep
You know, I think it's possible. I think you watch a fielder fielding a carom of a baseball, and they're making an estimate of where it's going to wind up based on experience and all that, but they are not making the assumption that it's going to go exactly where they expect. I do think that people do have a somewhat intuitive grasp of this stuff. And I think that if you make it too technical, they lose you.
Yeah.
But again, I would recommend this essay. Maybe I should Xerox it, photocopy it, whatever, scan it and send it to you. It's a wonderful little essay, and it deserves more prominence than it's gotten.
Remind us and inform Mike and Abby what the essay is.
It's an essay called The Nature of Knowledge. It's by R.A. Littleton, who was an astronomer. It was written in the 1970s. It's part of this book, the Encyclopedia of Ignorance, which is a collection of kind of off-the-wall essays about science.
But not pseudoscience.
No, it's a lot of it is by very, prominent scientists. John Archibald Wheeler, for you gravity people. Tommy Gold I mentioned Tommy Gold earlier. He put one in here. Yeah, it's just what are the puzzles? What are the weirdnesses? It's what don't we know?
Yeah.
It's a fun little book.
So
But he puts in this diagram of the bead on the wire, where what you do when you learn something about some topic, and you change your mind about how likely things are. You move the bead toward one end of the wire or the other as more information comes in, and you don't let it fall off the end, which is where all the problems occur. When you suddenly become sure and you're willing to defend to the death that certainty, you're in trouble.
your bead, you've lost your bead.
You've lost your bead.
Yeah.
Answer your question, Scott.
Yeah.
You can go ahead and finish, John.
Okay, I think I'm done, actually. Go ahead.
Okay. I guess, there are a lot of the books on cognitive bias give stories you know, either stories about, you know, experiments that were done, or case studies and, you know, failures and so on, which have memorable anecdotes, right, which might help people remember certain kinds of issues. So there's one that I remember in Thinking Fast and Slow by Daniel Kahneman, where he gives an example of, imagine you have it's a story where children, depressed children were given energy drinks, and 60 days later, fewer of them were depressed than at the beginning of the study. And this is an illustration of a cognitive bias called regression to the mean, which is, in order to be depressed, you have to be A, prone to depression, and B, unlucky enough to actually be depressed at the time. So at the end of the study, most of those students are not as unlucky as they were at the beginning. And that explains the difference, not the energy drinks.
I would have thought that a simple controlled trial would have told you that too.
Right, right. So there are anecdotes that explain it. I guess my point is not just that people are going to read about Bayesian reasoning and then go, oh, okay, and then they'll all be ideal reasoners, because I know that doesn't work because I can't do it.
But it's really hard to do it well. It's computationally intensive.
Yes.
The amount of supercomputer time that my friends who are your neighbors, do you know Don Lamb and Carlo Graziani? Okay, it's University of Chicago guys. The amount of computer time these guys use on their Bayesian analyses of astrophysical phenomena is enormous. The theorem looks very simple, but to apply it is actually quite difficult.
Right. I guess what I was going to say, Scott, is that maybe it doesn't really matter. You were talking about your AP English class as being one of the most important and memorable and one of your favorite classes in high school. I had a chemistry class that was my favorite. And it's the last chemistry class I ever took, in fact. So I don't remember explicitly a lot of chemistry. But I do know that chemistry is a study and that there are formulas for things. And so I don't go just going, if someone asks me a question about chemistry, I'm going to refer them to a chemist. If I need to create a chemical mixture for something, I'm going to go and find an expert, or I'm going to go and look it up. But if people don't even know that there is a way of thinking rationally, then what are they going to do? They're just going to go, I'm a smart guy. And
so you and I had a conversation offline a few weeks ago where we were talking about some of these topics. And one of the things that came up was the presumption that people want to be rational. My perspective on that is that people will consistently say they want to be rational, but I think most people don't have a deep desire to be rational. They have a deep desire to make sure their desires are justified.
They have a deep desire to be right.
Absolutely, yeah. So I think overcoming that entails one of my favorite topics, and that's humility, right? In order to be a scientist, and we have several here today.
Just have a few.
In order to be a scientist, you must develop in order to be successful. I mean, there are millions of scientists, and I'm sure there are exceptions to this, what I'm getting ready to say. But in order to be a successful scientist, in general, you must develop a very deliberate sort of humility, a humility in the face of evidence, a humility about your methodology, a humility about expertise in general, recognizing that you probably don't have it, that other people may know more about particular things than you do. And I believe that the combination of a deliberate practiced humility with a toolkit for doing reasoning more effectively in combination can do more than either one of them by themselves.
Yeah, I agree with you. And I think it's especially true in a way of theorists, because in particle physics, I mean, before we found the Higgs boson, there were hundreds of papers out there predicting different masses or didn't exist at all, and so on and so forth. Literally hundreds of papers from theorists. And basically, they were essentially all wrong. I mean, hardly any of them were right, but they have to accept the truth and move on, and the whole idea, you can reject wrong ideas, and you have to accept what nature tells you to, right? So, I mean, I've had ideas about, I thought, oh, great ideas, get excited about that, but if it's wrong, it's wrong. Accept it, move on.
Well, I think this is one of
Experiment's a bit different, because experimenters, if you're a good experimenter, you make good measurements, and you are, you estimate the uncertainties and so on and so forth. And of course, you work very hard to be sure that you don't publish anything wrong, but so that you don't have to eat humble pie and walk back. I mean, it's
Oh, come
sin.
on.
Okay, so
I think this is one of the things that we've all gone through as far as our papers and our dissertations and all these other things. We always start with the history. What has happened in the past that has led up to our particular research? And so that's the first part. The last part, after you get everything done, is what I did wrong and how many different ways are there that you can disprove me. I mean, topics for future discussion.
I remember your dissertation, you had a lot of, here are the ways that my study might be flawed.
Oh, and that's all of us. We all get there and we say, I could be so wrong. You can't believe how wrong I can be. So please go out there and A, reproduce my study. Is my study reproducible? And then B, go at it from a different direction and do it from a totally different angle. And if the two get together, we're beginning to say, we might be onto something. And then 100, 200 years from now, after everyone has studied it, maybe we'll be able to say, that's a pretty good idea.
Well, that gets back to Ivan's point about the accumulation of confirmatory and disconfirmatory evidence. And in inductive reasoning, you never reach a point of certainty.
Can't.
But what you can do is make and justify an argument of plausibility.
Yes.
That one hypothesis is more plausible than another.
And we've all been there.
Well, I made you laugh with my statement about not publishing wrong stuff. In my field, when I've probably been a co-author along with thousands of others of over 1,000 papers from the Large Hadron Collider, and I don't think any of them, maybe there are 2 or 3 or 4, maybe that should be retracted because they were. I doubt if even that number, because they go through such an intensive, rigorous checking, and they've got, everybody's putting their name on this paper. Maybe they've not read it, but they want to be damn sure that it's right. But if you are in a different field where you publish a paper with one name on or 2 or 3 names on only, then it doesn't go through that very rigorous checking. And
when you're in a field where you're looking at things in the sky that are changing, and you got to get the info out quickly, because if you don't, nobody's going to look at it and tell you whether you're right or wrong. You're wrong a lot because you're in a hurry. You don't have time for all this checking.
Right.
I mean, I had one. We had a rotating authorship deal on some alerts, and I wound up as first author on an alert that was completely bogus, because I was in the rotation, but I happened to be on an airplane out of communication at the time. And I probably would have caught the mistake and probably would have said, nope, that's bogus, if I'd been there, because that was, my particular expertise. But I didn't get a chance, and they threw it out with my name on it.
John, are you talking about alerts or published papers in refereed journals? I mean,
I'm talking about alerts, but those are publications. Those are for the stuff I do. They're as valuable as refereed papers, because without them, we wouldn't study phenomena like gamma ray bursts.
So what you're saying, John, is that you got the credit for a mistake that you didn't make.
Yes.
Wow.
Well, I was part of the team.
Yeah.
Teamwork. Sometimes I get more credit than I deserve. Sometimes I get less.
But Mike,
I
Mike,
remember
when you
one.
say-
I remember one time when I presented a result, and one of the experts in the field said, "That can't be right. That's," and she criticized my data analysis technique as witchcraft. And then she went back and she actually had better data, and she looked at it, and I was right.
Oh,
So, you know, it works both ways, and it's fun, and you got to enjoy the process. And to be a good scientist, you've got to get a real thrill about being wrong.
Yes.
Wow, I thought I knew that, but nature surprised me. This is cool.
Yeah. Ivan, you had something to say?
I was just going to say, Mike, when you said that all these wrong papers, I mean, I remember as a grad student writing papers about what would the CP asymmetry be in this experiment if model X were true. So we probably did the calculation correctly, but the probability that model X was true may have been infinitesimal, right? So it wasn't wrong. But maybe it was speculative without using the word speculative.
Well, it sounds more deductive, right? Given the rules of the game specified as X and Y, here is a conclusion we can draw from that.
Right.
But
right.
it presumes that X and Y have some relevance to nature.
that's the old deductive reasoning problem.
Well, and to an experimentalist, those papers are actually, those theoretical papers are actually valuable because they say, oh, you should see this. And
Yeah.
that's something I can go and look for. And
So
that's what we did with gamma ray bursts. I started working on gamma ray bursts when there were more hypotheses about what they were than there were observed gamma ray bursts.
Right.
But the hypotheses had consequences. And so you could look for those consequences and see.
Well, that's the thing about sticking your neck out. If you actually stick your neck out and make, as you said, point in a given direction, say, oh, you should look at this or you should look at that. That's an important aspect of the whole humility thing, is look here. And then somebody may actually go look there and find out that what you thought was right was completely wrong. And, you have to live with that.
But, human nature being what it is, I mean, experimental physics, you want to be the first to actually see something new or discover something, and it can get so exciting, and it can cloud your judgment in a way, but because you want to get it out there and get the credit for it if you want. I mean, I've seen, in my Tevatron experiment, okay, we had a paper was coming out about the spectrum of high energy jets of particles coming out, and it went all the way out to hundreds of GeV. And I remember saying to the student who did that, have you looked at these events, on a display to see what they look like actually? No, he hadn't done that. He just got plots from the computer program. So I said, well, maybe we should look at that. So I sat down with him and we got this display program. And the top event, it looked crazy. It looked so weird. We didn't understand it at all.
When you say the top event, do you mean the event?
The highest energy event. Okay.
Okay, thank you.
So it had a jet of particles with a transverse energy, that sideways energy of several hundred GeV. And it was really way out there in the tail. I said, we should study the highest energy 20 events or so and see what they look like. And then I went away and I came back a week later. Have you looked at them? He said, well, I've looked at the first 3. I said, okay, well, let's look at them. And 2 of them were really blowing my mind. I thought, my God, it looks like a new particle, a new pair of particles coming out that we've never seen before. I got so excited about it. You start writing a paper about it. Of course, then the whole collaboration comes and say, okay, they've got to tear it apart and really try and prove that it's not that. Anyway, it turned out that in the end, what it was, we understood it to be probably a very high energy neutrino that had come through horizontally, a cosmic ray thing coming through the apparatus, And anyway, long story short, there are a couple of these events in 2 years of running. And that's about what you might expect for these high energy neutrinos. Okay, but I know from experience, you think, my God, I've got a discovery here, this is going to be great, Nobel Prize, blah, 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 blah. But
in the team like that, the whole team comes in and tries to find explanations for this, So,
I have
go ahead.
I have a question. Maybe we can bring Abby in on the discussion as well. Why is it that in particle physics we need to collect millions of examples of a thing in order to be confident in it, but it only took one observation of Tiktaalik to draw a conclusion about the science related to evolution? Why does one science require vastly more observational evidence in quantity-wise, the number of observations, than some other science?
No, it depends on what you call signal to background. Now, the Z boson, the W boson, we discovered with a handful of events, really, 5 or 6 events, actually. That was a discovery because there's essentially no other process that could fake the observations here. There was a famous particle called the omega minus, which was found at Brookhaven in a bubble chamber picture, and sort of confirmed the quark model because Gell-Mann had predicted this. One event in a bubble chamber, but with all those tracks. Now, the Higgs boson, to find that, required tens of thousands of events because its most clean decay mode was to 2 photons, and there's so many other processes can produce 2 photons. So you had a distribution, and you had to look for a bump in this distribution that was, 5 standard deviations and so on and so forth. So because the background was so high, it required a very large number of events, and the production, it's a very rare process to produce it as well. So you have 1 billion collisions per second going on there at the Large Hadron Collider, and out of that billion, a few of them, a handful, make a Higgs boson.
So in physiology and evolution and anatomy, sometimes spotting a single anomalous example can lend credence to a hypothesis. The idea that according to the very fundamental notion of natural selection, at some point a lobe-finned fish should have begun the transition to a limbed creature that can walk instead of swim, primarily walk instead of swim. Darwinian natural selection says because of things happening in graduated continuous shifts, there should be some intermediate between a lobe-finned thing and a walking thing. And they found one example, Tiktaalik, in the high Arctic, and said, aha, we have evidence that corroborates this theory of evolution about intermediate stages. So they didn't have to find a million events. I don't know that background noise is relevant. Why is it that some scientific things require only one example?
Well, in the case of Tiktaalik, there it was. It was physically there. You could look at it and go, and everyone could look at it. Whereas in the case of the Higgs boson, there's an action there, and you don't know it. You don't know it until you get all the statistics built in, and it's not just from one detector, as Mike will point out. There were 2 separate detectors looking at this world from 2 completely separate points of view, and they had to have both of them have this very, very high degree of statistical, 5 sigma, just to say yes. So one case, there it is. You can physically pick it up and look at it, and everyone else in the world can look at it. And in the other case, it's a statistical analysis.
Well, with Tiktaalik, as Joanna was saying, the signal to noise ratio is very different because you clearly have something when you have that fossil in front of you. But there are a few things that you glanced over there that are also very important. With the sea-land transition, in fact, there are a bunch of things to talk about here. With the sea-land transition, that had already happened at least once. Vertebrates were not the first land animals, so arthropods were. So basically, bugs beat us to the land, very handily, by the way. And there are lots of other fish that spend some time on land, and you can walk around and see them today. I don't know that we would quite call them transitional species. They're more like species that like shallow water. But the point is, they do it. One of my favorite animals in the entire world are mud skippers, which are walking fish, basically. Am I being heard, by the way? Everything's frozen.
Broke up a bit, but yeah, it's okay.
Yeah, you're okay.
Anyway, so as I said, there are walking fish extant today. In terms of transitional species, there are lots of transitional species. I mean, kind of the most famous one is Archaeopteryx. And when one of those was found, it was big news, but then they found a few more from time to time. But in this case, it wasn't just that it was a walking fish, but that there were predictions that had been made about the particular line of vertebrate fish that we thought would transition into, land vertebrates. And, we thought we knew when that happened. We thought we knew where that happened. And so then they basically had to go off and look for that particular kind of animal. And they predicted that there would be that particular kind of animal in that particular place.
Mm.
And they weren't living in the Arctic at the time, but, plates move around. And they were able to find it. And it was, to a great degree, exactly what they had predicted. And it had those wrist bones that they were supposed to have and all that kind of good stuff.
Yeah.
So, it was again, kind of what I was talking about with that business of being willing to stick your neck out and make a prediction. And, they were fortunate really only in so far as it's not easy to find fossils.
Mm.
And they found the fossil. But as I said, there was a lot of, work and prediction and so on that made finding Tiktaalik much more exciting.
Ivan, does that play? Go ahead.
I wanted to point out something else. Just recently, there was a paper that was published talking about a single gene in a zebrafish, which if you change it, the zebrafish went from fins to feet.
Wow.
Just
There's so much fantastic stuff about fish limbs. And there are fish that live on shallow seafloors now that have what amount to feet on the bottom of their bodies. And instead of swimming along in shallow water, they more or less walk weightless in shallow water. And, that's how they get around. So this is not an uncommon phenomenon at all.
And then we have flying fish too, right? We have fish who fly with wings. I mean,
And
Yeah.
birds that swim.
And as I said, these mud skippers I've been talking about, you've got to love them. They also climb trees.
yes.
Yeah. I want to do a
Yet other species that have suckers. So, I mean, and you can find videos of all these things online. It's wonderful, where they actually crawl up rocks in freshwater streams. So, there will be water flow, small waterfalls with fish climbing up the waterfalls on the rocks. So, it's pretty amazing.
spiderfish.
Right. So, and I think that this maybe is a little bit of leftover religious thinking where, we tend to think that there are these hard and fast categories, these are fish and these are land animals and all this kind of thing. And fish are just very creative. They are, they come up with all kinds of ways of sometimes being in the land and sometimes being in the water and sometimes being in the air and sometimes climbing trees. I mean, they do a lot.
Yeah. I want to do a sort of not really a public service announcement, but remind people that this is a program sponsored by the American Humanist Association. And we talk about things on the intersection of secularism and science. We talk about the scientific method and scientific discoveries. And if you're out there watching us live today, and you have a question about anything we've been talking about, or just any question about science or the philosophy of science that tickles your fancy, feel free to type in your question on the YouTube chat or connect via the link shown on the YouTube live stream. And we can take your questions. So back to our regularly scheduled program. Ivan, do you have Do you have any insight from a Bayesian perspective about things that require one piece of strong evidence like Tiktaalik versus things that require the statistical accumulation of evidence like particle physics?
So like the theory, a modern understanding of evolutionary biology does not depend on Tiktaalik, right? So we didn't prove evolution with Tiktaalik, but we probably did give a lot more credence to a particular model of what was going on within evolutionary biology. So in Bayesian reasoning, there are generally two components in calculating what your new probability is for, or what your new confidence is in a theory, given some new piece of evidence. And the first ingredient is, what was your confidence in the theory before you got this evidence? And that is a sort of a representation of all the evidence that has come before. And then the next factor is, what is the probability of seeing this evidence in this, in one theory versus in the competing theories?
Can we talk about intelligent design? Would Tiktaalik be consistent with a theory of intelligent design versus evolution? So you have to be extremely careful when you say the evidence is consistent with. Okay.
Right? With the dice game that I played before, 6-sided die, 20-sided die, I roll the die, I got a 4. That's consistent with the 20-sided die. Yeah, it's consistent, but it's actually less probable. Right?
Ivan, so
the trouble with intelligent design is that it's kind of like an infinite-sided die.
Well,
because God can do anything he wants.
Yeah.
Oh, another problem with intelligent design is that it absolutely cannot make a prediction.
Well, that's what I'm saying. It's an infinite-sided die.
Prediction.
So I have a question for Ivan, if I may, because I'm not an expert on Bayesian statistics and so on, but here's a question. There's something that has an answer that we don't know if it's between 1 or about 100 billion. It's somewhere. Now, this is the number of planets in our galaxy that have life. Okay, we know it's 1. We know it's 1. It could be 1. It's very unlikely to be 2 or 3. If it's more than 1, it's probably thousands or millions. Okay. If we find evidence that there was life on Mars or has been life on Mars and are not connected with life on Earth because they communicated or something like that, then it makes it extremely likely that there's life on, 100,000 million planets in the galaxy. But right now we don't know. It could be 1. Okay. So I suppose this is a sort of Bayesian question, It's very unlikely that there's only 2 or 3 planets in the galaxy with life. It's extremely unlikely because if it happens more than once, it might probably happen thousands of times. Would you comment on that?
So one of the reasons why we think that it's very likely to be a lot of planets is that life formed so rapidly after it was possible for it to form on Earth. Right? That I think it's estimated that it was within like 100 or 200 million years, which is a very small time. So
infinitesimally small.
So yes, what you would do in order to think like a Bayesian, the first thing to do is to lay down what are your competing theories, and then say, what do these theories predict as far as the evidence is concerned? And I think that one of the challenges in trying to figure out whether there is life on many planets is there are a lot of possible models that you can come up with. It's almost like you have, a billion different models that you might put together with different ratios in them, right? But if you're going to split them, like come up with some arbitrary number, right, that describes your model and say, is it larger or smaller than this? You need to create models which are mutually exclusive, and then look for what those models predict about the formation of life, independent formation of life on Mars versus, Mars and Earth, and then put that into your Bayesian formula, and that will tell you, okay, now we know which of these two models is more probable and by how much. Now, part of this obviously comes down to our prior probability. Like, what should we put in as our initial belief, right? Is our initial belief that life elsewhere in the universe or elsewhere in the galaxy is very likely? Or should we put in that it's 50-50? And so Bayesian reasoning, in general, those priors are taken to be subjective, which means that you don't have to have an exact prior. Like, you can use some subjectivity in it. You can't use arbitrarily as much as you like, right? Because if you did, you could just say, well, my prior is virtually zero, so I don't have to move my numbers at all. But usually you want to come up with some sort of justification for why you chose the prior that you did.
Yeah, but here's my problem. So about this life question, Mr. A can say, I believe there's only one planet in the galaxy with life, and that's us. Mr. B can say, I believe that there's millions of them or billions of them. So they're two completely different beliefs, and how do they fit in?
Well, there's quite a bit of literature on choosing a maximal, a prior that represents your ignorance. It is a tricky problem. You can't start from nothing in Bayesian inference. But, the Bayesians would say, well, but when we look at, say, frequentist methods for estimating things, it turns out that the frequentists have priors too. They just don't explicitly identify them. So yes, you have to start from someplace. You have to start from the idea that your coin is probably unbiased, but maybe it's biased. And so you give it a prior, and then you flip it a bunch of times, and eventually you'll have a pretty good idea of whether it's biased or not. But you have to include in your prior everything that's possible.
Yeah. I really like, Mike, I really love the point you made about if evidence for life is found on Mars, if that evidence exhibits characteristics that are very similar or identical to the characteristics of life on Earth in terms of the way that DNA sequences code for particular amino acids, and there's only 23 or however many there are. If it's found that Mars has essentially the same chemistry and formula for life, assuming that some sort of evidence of life is found in the first place, then I really like the point you made that doesn't allow us to draw any really remarkable conclusions, because it very well could be that a blasted off piece of rock went from one place to the other. But if it's remarkably different or noticeably different than the chemistry of life on Earth, then that's a whole new ballgame. That is really a fundamental shift in what we know about the universe just from that piece of evidence.
Well, this comes back to Ivan's point that life apparently originated relatively soon after Earth's conditions allowed it to. But did life originate only once? Because if it only originated once, and we're all descended from that first, primeval organisms, then why only once? I mean, that makes it a very rare occurrence. If it was relatively easy for life to start, abiogenesis or whatever, then you'd expect to have many which would have opposite, half right-handed and half left-handed helixes in their DNA or proteins or whatever, because physics doesn't tell you one or the other. I mean, at least we do know that there is a weak interaction difference between right and left-handed stuff, but nobody knows how that would tend to favor molecules of one type or the other.
Yeah, did you see the have you seen some of the speculations that the early polarized light from the sun selectively favored primordial organic molecules of a particular sort of twist or helicity, so that the early sun is speculated to have had more polarized light, and the polarized light that happened to come out of the sun might have selected for particular polarized molecules.
No, wait, I don't understand that really. I mean, I don't believe that. Have they actually a mechanism for the sun emitting polarized light? I don't believe it does, or how it can. I mean, the atmosphere scatters light in a polarized fashion. So light from the sky has polarization. That's happening on Earth. But are they do they actually have a mechanism by which light being polarized can favor left-handed or right-handed molecules? I think this is probably just saying, well, maybe that's a possibility, but there's no mechanism.
Yeah, I'm not aware of this hypothesis. I do note that the early sun probably had a much higher magnetic field, and yes, you can get polarization effects in strong magnetic fields, and in particular, you can circularly polarize things, which is what you would have to do. You can circularly polarize light, which is what you'd have to do to separate left and right. But on the other hand, the sun's magnetic field is tangled, and it's as likely to be pointing a north pole at you as a south pole. So I don't know how that would particularly favor one helicity over the other. But
yeah, it's a speculation that I read about a few years ago. But the point is that again, in the context of Bayesian reasoning, having a hypothesis that, you know, Mike's hypothesis is incredibly insightful, that if life arose easily and quickly on Earth one time, and manifestly it did, then why didn't life with slightly different chemical properties arise many times? And if it did, where is that life? Maybe it was destroyed in situ on planet Earth, maybe it was outcompeted, or maybe it never arose in the first place, in which case you have to look for an external cause.
Yeah, I would speculate strictly on the point of view of a chemist that it occurred many times and in many different ways. And there was simply a chemistry competition going on here, which had the greater probability of existing versus something else. Was one set of molecules more liable, which was more easily created? And whichever avenue had the longer lifespan, was more easily created, that's the one that wins.
Yeah.
And so here we are.
Isn't chemistry absolutely left-right symmetric? I mean, aren't all chemical reactions identical in the mirror as they are? I mean,
yeah, and then of course you get into the whole thing of racemic mixtures and versus the biological. So if we were to make an amino acid in the laboratory, it would be a totally racemic mixture. It'd be half right-handed, half left-handed. But then the biology comes in and says, oh, no, we only have one. We only have the left-handed version. But there's also a whole series of molecules, for instance, alcohols, which are totally right-handed. So is there a left-hand versus right-hand bias? No, it looks like it's just that.
In chemistry.
In chemistry, as far as biology is concerned, there is a difference between right hand and left hand. In chemistry, no, they're the same thing.
Yeah.
Trying to channel Stephen Jay Gould here, I would point out that in the paleontology we know, nearly every lineage of living things has died out.
Right.
Right.
So it is not inconceivable that there were multiple lineages in the beginning and only one survived.
Yeah, that would not be surprising at all, both just from competition, but also just bad luck and other things.
Yeah, well, Stephen Jay Gould, of course, talks about luck.
Yeah.
The right hand, the left-handed wins because it's lucky, and the right hand loses because it's unlucky. That is one of the mechanisms he talks about. And if you look at the evolutionary dynamicists who've turned this all into mathematics, luck is a huge part of it.
Yeah. Abby, we are at the end of our allocated time for today. Abby, maybe if that's okay, I'll give you the last word. It looked like you had a comment on what we were talking about here.
Well, I was just going to say that the life and deep sea vents, which has been at least kind of sort of separated from life elsewhere, is different, including different in its chemistry in a couple of ways that I can remember, including one that was pretty basic, and I wish I could remember exactly what it was, but it was like they don't use ATP, I think was what one of them was. And I mean, that's pretty fundamental to how life elsewhere on the planet works. I cannot comment on, whether they have helixes that go one way or another, because I truly don't know, and it may be that we haven't looked. So if they have DNA or RNA and which way it twists, I couldn't tell you. But as I said, I do remember that there was some very fundamental stuff having to do with energy usage that actually was different
That's
in
surprising.
creatures.
Yeah.
Well, they are really, they're different in a lot of ways. They actually don't use the sun for energy. They actually get their energy from chemosynthesis rather than photosynthesis. And they've been separated just in terms of being able to communicate with most other life pretty effectively by their location. So they are sort of these isolated populations with very different things that were either in their favor or not in their favor. Very different situations they were dealing with. I was also just going to say briefly, really looping back to what you're talking about earlier with Tiktaalik and evolution and all of that kind of stuff. There was and is actually a whole lot of statistical evidence for evolution as well. And this came up very early on with botanical evidence. As the nice thing about botany is that the plants hold still, and you can get 1,000 specimens in a day in botany, and you can do species distributions. And there was so much early evidence for evolution that was based on species distributions.
Oh, wow.
That there are a lot of, like plants, that's where a lot of the most convincing early evolution actually came from.
Thank you very much. And that circles back to Ivan's topic about accumulating evidence in support of a hypothesis. So
yeah, and you can accumulate a lot of evidence in botany. It's nice that way. So,
all right. Well, thank you all for joining. Really wonderful conversation.
What a great conversation.
We're going to try to do this in the future, have sort of a thematic approach, one or two themes for our discussion, instead of just sort of rifling through recent science news. And hopefully that will be more engaging for our listeners and viewers. So thank you all for joining us.
Great to see you guys.
Good luck
Be
with your
well.
book, Ivan.
Thank you.
Right.
and I appreciate seeing that essay that John was talking about.
Yeah, John, send out that essay to us, and if I find out something about the polarization of molecules and sunlight, I'll send that out.
Okay.
Yeah.
Take care.
Bye, guys.
Bye.